Hi there, this is lecture 11, section 4.3 on the product and quotient rules. So up until this point, we have our four basic rules that allow us to manage constants, powers, addition and subtraction, and constant multiplication. Okay, so what we haven't dealt with is what happens if you multiply two functions together. Can we just take the derivative of each piece and multiply them together, much like we do with addition and subtraction, or does it need to be more complicated than that? So let's take a look. So let's look at an example, in this case, the 2x minus 7 times x squared plus 3x. Okay, and we're going to try doing this the long way. So right now, we don't have rules for multiplication. So in order to do this, we would have to say, okay, let's distribute this. This is the same as 2x cubed plus 6x squared minus 7x squared minus 21x. So that's the same as 2x cubed minus x squared minus 21x. So when I go and take the derivative, we end up with 6x squared minus 2x minus 21, right? So three terms there. Not too bad, manageable. Now the idea here is that we want to have a rule for multiplication because not every time I'm multiplying two functions can I multiply them out and get rid of multiplication, right? If I took an x times an e to the x, that's not going to let me do it. I'm always going to have those two multiplied together, so I need to have a rule for multiplication. Well, my first thought is that if our function stays multiplication, 2x minus 7 times x squared plus 3x, what if we did just like we did with addition and say, okay, well, can I take the derivative and just take the derivative of each piece and multiply those two together? So the derivative of 2x minus 7 would be 2. And the derivative of x squared plus 3x would be 2x plus 3. And that would give me 4x plus 6. Okay, well, that would be great, except those two are definitely not the same, okay? We know that the one on the left has to be right because that always works, right? We can multiply it out and take our derivative and that should work. So what that means is that the idea of a shortcut rule doesn't work. So this is a big no-go, right? So we don't want to do that. So the question is, what do we want to do? Okay, so we know, and take a look at the notation here. If we have a function g times a function k, and then we take its derivative, that's not the same as if we took the derivative of the first one times the derivative of the second one. Okay, I just showed you that that does not work. So the question is, what does work? So when we need to find derivative rules, we go back to the limit definition. Okay, so we're going to say, let's suppose we have f of x equals g of x times k of x. So I have one function times a second function. And I want to find its derivative. So that means I want to find f prime, and I'm going to zoom in here. This is going to take a little bit of space. I'm going to find f prime is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, and I'm going to follow this through exactly how we would have done it in class. So let's plug it in. So f of x plus h just means I plug in x plus h where I see x's. So this is g of x plus h, k of x plus h, minus the function itself, which is g of x, k of x, all over h. Okay, no problems. Okay, except now what we would normally do next is simplify and factor, which I can't do, right? They don't have anything in common. So what I'm going to do is I'm going to put in and take out a term so that I have more stuff to work with. So I'm going to keep my g of x plus h times k of x plus h. And then what I'm going to do is I'm going to subtract g of x times k of x plus h. Okay, so I subtracted a term. Now I'm going to add it back in. And then, of course, I have the minus g of x, k of x from before. Okay, now what does that do for me? Notice that the two red terms cancel each other out. So I have not changed the limit. So that makes this legal. But I added stuff so I have more things to work with. So what I'm going to do is I'm going to look at these first two and notice that they have a k times x plus h in common. So I'm going to make this the limit as h goes to 0, and I'm going to take out a k of x plus h. And when I do that, I have g of x plus h minus g of x left. And then over here, when I look at these two, they both have a g of x in common. So I'm going to add, and I'm going to take out the g of x. They have a k of x plus h minus k of x left. And all of that is over h. Okay, and now I'm going to start splitting some stuff up. So I'm going to split up my fraction, and so each piece of the addition gets its own h and its own limit, right? And I'm allowed to do that because of limit laws and things like that. So we have a k of x plus h times a g of x plus h minus g of x, and that's where I'm going to put the h on the bottom. Plus the limit as h goes to 0 of g of x times k of x plus h minus k of x all over h. Okay. And now we can start to look at what this is. So let's see. Let's talk about this piece and this piece for a second. So on the left, the k of x plus h, if you let h go to 0, that's just k of x. And g of x actually doesn't have any h's at all. So when you let h go to 0, that stays g of x. But then let's take a look at these. So we're taking the limit of each of these pieces as h goes to 0. But that looks an awful lot like the definition of the derivative, only the function on the left side is g, and the function on the right side is k. And that's exactly what it is. So what's in blue on the left there is g prime of x. And over here, it's k prime of x. So here's what we end up with. We end up with that f prime of x is, and I'm going to reorder them because I'm allowed to write when I'm multiplying and adding, I can reorder. So this is g prime of x times k of x plus k prime of x g of x. So what I do, this is what becomes the product rule. Okay, if I take away the of x's part, this is f prime equals g prime k plus k prime g. So notice that I'm taking the derivative of the first piece times the second plus the derivative of the second times the first. Okay, and that's going to become our product rule. And that's exactly what you have here. Now, I think it gets a little bit confusing with letters and k's and x's and all kinds of stuff. So I think about it in terms of numbers. So if I have a function that's written as two functions being multiplied together, function 1 times function 2, I think of the product rule as 1 prime 2 plus 2 prime 1. It's easy to say, and it's easier to write out. So in this case, this was our example from above. The way I would do this is I would say, okay, this one here is my function 1. And this one is function 2. So I'm going to write it out. Function 1 is 2x minus 7, and its derivative, 1 prime, is going to be just the derivative of 2x minus 7 is 2. For function 2, I have x squared plus 3x, and the derivative of that is 2x plus 3. And then I use my product rule to put it all together to find f prime of x. And I take 1 prime 2, which are these two multiplied together. So that's 2x minus 7 and 2x plus 3 being multiplied together. Plus these two multiplied together. So 2 times x squared plus 3x. And if I distribute this and combine like terms, I should get what I got above. So this is 4x squared minus 14x plus 6x minus 21 plus 2x squared plus 6x. And if I combine my terms, this is x squareds, x's, and just a constant. So that's going to leave me with 6x squared minus 2x right? 6 and 6 is 12, negative 14 and 12 is 2, and minus 21. Now let's check. Is that what we got when we did it the surefire way up above? 6x squared minus 2x minus 21. So we do get exactly the same answer. So that is our procedure for product rule when we're multiplying two functions together. Now, you're going to tell me, why didn't I just multiply it out to begin with and take the derivative? It's quicker. The answer to that is yes, it absolutely is. And when you come across this one on a test, I'd probably do it that way. However, what I'm trying to show you is that in the future, we are going to be in situations where you cannot multiply and combine like terms, right? You still have two things multiplied together. So we've got to learn the product rule to be able to manage that. And the easiest way to do that is when you're working with things that you're comfortable with, like polynomials. Okay, so that's the method to my madness. Let's take a look at a second example here. Function 1 would be this part. Function 2 would be this part in parentheses. Okay. Now, when I go to write this, I'm going to rewrite these because notice these are not in differentiable form, right? They're not powers. So I need to fix that when I write it down. So function 1, when I write it, 1 over x squared, I'm going to write as x to the negative 2. Its derivative then is, whoa, sorry, we're jumping around, negative 2. X to the negative 3, right? Multiply by your exponent, subtract 1 from your exponent. On the red side, for function 2, I have x squared plus, and the square root of x, I'm going to write as x to the 1/2. So that when I find my 2 prime, that's 2x, right? That one's not a problem. And then plus 1/2 x to the minus 1/2. Right? We'll get used to that one pretty regularly. We bring down our 1/2, multiply by the 1/2, subtract 1 from the exponent. And then I put this all together using my product rule. So f prime of x equals 1 prime 2 plus 2 prime 1. So I'm taking 1 prime 2, that's these two. So I have negative 2 x to the negative 3 times x squared plus x to the 1/2. Plus, then I have these two multiplied together. So that's x to the negative 2 times 2x plus 1/2 x to the minus 1/2. All right, now this looks messy, but we're going to clean it up. So we're going to distribute here. So you're taking this one times this one. So that's negative 2, and I'm taking x, and I'm adding powers. So negative 3 plus 2 is negative 1. Then I'm distributing to this term. So that's minus 2x, and now I'm taking negative 3 plus 1/2. Okay, negative 3 is negative 6/2, plus 1/2 is negative 5/2. This is my first two terms. Over here, I'm distributing my x to the negative 2 times the 2x. That gives me a 2, and I'm taking, there's a 1 right there, so negative 2 plus 1 is negative 1. And then lastly, I'm taking the x to the negative 2 times the 1/2 x to the negative 1/2. So that's plus 1 times 1/2 is 1/2. We multiply the numbers. We add the exponents on the x's. So negative 2 plus negative 1/2 is negative 5/2. What that means is that these two can be combined. So that's going to give me, oh, and these two can be combined. In fact, these two can cancel because one's 2x to the negative 1/2, and one's negative 2x to the negative 1. So then I just get, let's see, negative 2 plus 1/2 is negative 3/2, x to the negative 5/2. And I want to move that x down with the 2, so it's negative 3 over 2x to the 5/2. And that is my derivative. Okay, so that's how product rule works. Similarly, we need to be able to handle division, right? So the long way for x squared plus x minus 1 all over x would be we would divide through by that x. So it would be x plus 1 minus 1 over x, which I would write as x plus 1 minus x to the negative 1. And then we would take the derivative. So the derivative would be 1 plus x to the negative 2, which is 1 plus 1 over x. That's my derivative. Now, we'd like to be able to say, okay, well, if we have f of x equals x squared plus x minus 1 all over x, can't I just, in order to find my derivative, take the derivative of the top, which is 2x plus 1, and divide it by the derivative of the bottom, which is 1, and get 2x plus 1? Well, can I? No, these two do not match, right? One has fractions and one doesn't. So that's not going to work again. Sorry, give me a minute. So these two clearly don't match. So what we need is a quotient rule, right? So this looks similar to what we had before. If you have a g of x over a k of x, we have g prime k minus k prime g all over k squared. So main differences between product rule and quotient rule is that we've got minus and you've got a k squared on the bottom. Okay, I like to think of it as top prime bottom minus bottom prime top all over bottom squared. Okay, so from there, we're going to go through these last two examples. So that means that function, the top is the x squared plus x minus 1, and its derivative is 2x plus 1. The bottom is just x, and its derivative is 1. So when I put the quotient rule together, I need top prime bottom minus bottom prime top over the bottom squared. So I want top prime bottom, so these two, x times 2x plus 1, minus these two. Watch your parentheses here, parentheses x squared plus x minus 1. All over the bottom squared, so that's x squared. And if I distribute, that's 2x squared plus x minus x squared minus x plus 1. And that turns out to be x squared, my x's cancel, plus 1 over x squared. And if you divide that one through, you get 1 plus 1 over x squared, which is exactly what we had above. So that one works. Similarly, for our second example, the top is the 2x minus 7. The top prime is 2. The bottom is x squared plus 4. And the bottom prime is 2x. So when I put this together using my quotient rule, I want top prime bottom. So 2 times x squared plus 4 minus bottom prime top, which is 2x, times 2x minus 7, all over the bottom squared, which is x squared plus 4 squared. I would never multiply out your denominator. It just doesn't help you. But I do multiply out the numerators so that I can combine like terms if I can. If I combine like terms here, this gives me negative 2x squared plus 14x plus 8 all over x squared plus 4 squared.